Okay, so let's move to the LHC and the Higgs. Now, the Higgs is the boson that was missing in the table that we had before, but it is not the same kind of boson like the other bosons we talked about. We talked about bosons with spin 1. This one has a spin 0. We have not discovered a particle with spin 0 elementary ever. This is the first one. And we think it's elementary, but we're still working to figure out whether it is yes or no. Now, in these words that I have up there, I call the Higgs also a new force of nature. And the nomenclature is a little bit mixed up because the forces we note as the ones that are carried by gauge bosons, which are the W's, the Z's, and the photons, and not by, and the gluon, and not by a spin 0 boson. But for all practical purposes, you can change a little bit the nomenclature and call the Higgs a force, a new fundamental force. Let me show you a little bit how an aerial of going down to the LHC, 27 kilometers around, in between Switzerland and France. My office is somewhere there at CERN, close to the airport, and now we're going to go underground, about 100 meters underground, both experiments. This is the Atlas experiment, which is in Switzerland. And this experiment was built in situ there, and what we're looking is a time lapse of 4 years where the experiment was built, a part of the detector was built. What we're looking inside is the calorimeter, and this arachnoid structure around is nothing but a toroidal magnet. The magnet is used in order to bend the particles, because when you bend the particles, you can figure out their momenta, and this is why you have the magnets. And this is the tunnel. There's about 1,300 of these dipoles, 14 meters each. The dipole technology is pretty amazing. Within the same magnet, you have beams of protons and protons going the other way in order to collide within the same magnetic field. This is highly non-trivial. This was discovered by John Blewett at Brookhaven Laboratory in 1970, and it was not picked as a technology for the SSE. The SSE was 2 tunnels with 2 different beam pipes. This one is 1 beam pipe, which is only splitting at the experiments. And it's an amazing technology to actually build this type of magnets that will do this. Now, what we saw in the movie was also another kind of pipe you saw there, and this is the pipe of the liquid helium. I said that the magnets are superconducting magnets, and they produce the field needed for the protons to remain around the ring and be brought to the very high energies. And the superconducting magnets, they need about 9 tons of helium in order to be operating. This is the biggest density of helium in the entire universe, and also why helium got so expensive. All right, so here is something about particle interactions. If we in this little graphic, we see first we saw a muon going through the detector. On the middle is a silicon camera, and in the intermediate layers there are layers of detectors that detect electromagnetic radiation, the hadronic particles, as well as the muons that went through the steel and go through the chambers that we saw outside. Each particle, when it interacts with each detector, leaves a different signature. There are about 100 million channels in this detector that collect the signals from each detector where a particle went through. And when you reconstruct all of these hits of all of these particles that went through in a collision, you reconstruct what we call an event. The detectors are very giant. This is the other detector. I showed you Atlas before. This is the CMS detector. And the CMS detector, unlike the Atlas one, was built on the surface, and then it was brought down. and it was built in 12 different pieces, like a Lego. The heaviest of these was a 5,000 piece, which had the magnet, and in our case, CMS means compact muon solenoid. The magnet was a solenoidal magnet. All right, so this is the day this is the day after the first collisions in September 2008. The first collisions were September 12, and September 18, we blew it up, as you remember. And the Lynn Evans is on the right, and I am on the left, and my hair is unwashed, and his hair is uncombed, and we're talking about the success of the machine, also being worried about when we are going to have collisions in the detector. Then we blew it, we fixed it, and there we are in December of the next year. I was running the first shift where we took data at the highest energy. We beat the energy of the tevatron. This was a 2.6 TeV. And now the difference is that and despite the fact that I was on night shift, you see I'm dressed well, I have my hair is washed, so you can imagine what happened. My mom and dad were there, and in the middle of the night, we woke up the spokesperson, Jim Verdi, in order to make a record of the fact that we were the first to take the highest energy collision. So we were very excited. Now, the particle discovery is within the time of the LHC. I want to show you that in 9 months of the LHC, we have rediscovered all the particles of the standard model from a century. So the machine, the first thing that you do when you bring a new machine up is you try to verify everything that you know so far and that it is correct. And so we have done that in a very fast period of time, from 9 months running and a few months of cosmic ray data. And we had a visit, of course, from Peter Higgs, because the LHC was built to discover the Higgs. That was the main mission of the experiments. Both Atlas and CMS were designed, each of the elements of the detector was designed such that we are able to identify a Higgs in a mass range that it is very huge, from 100 GeV all the way to a TeV and more. It is important to keep in mind that the Higgs is, the hunt for the Higgs is not just at the LHC, that we had decades. In fact, the largest time for the hunt of the Higgs was at experiments before at the tevatron at Fermilab in Batavia, Illinois, and before that back in Geneva at the lab. And experiment by experiment and data period by data period, we narrowed the window. All these stripes that you see, the colored stripes, the vertical colored stripes, are exclusion regions where the Higgs is not. And there was this little slither that was left here that was allowed for the Higgs. And look where it is between 122 and 126. And this came in 2011 when we had the first LHC run. So I want to put a little bit of emphasis on the data, because we are, the LHC, this is in fact a picture from the Department of Defense. The internet before the LHC around 2008 is one little dot, one pixel in this superhighway of data, according to the DOE, and it's true in terms of data transfers, of networking, of distribution of data, the grid, and between 2008 and now, we have learned from building the computing system of the LHC, we have learned a lot. The thing to remember here is that we are susceptible to between 100 terabytes per second to 1 petabyte per second of data. This is a lot of data. It's no comparison to the data that Google is handling, and so Of course, with the advent of all the social media, there is now data everywhere of that sort of magnitude. On the right is a little graphic that shows you the data of the LHC compared with the tweets per year in 2011, the human memory, the World of Warcraft servers, the US Library of Congress, and Wikipedia, where Wikipedia is a dot, and the Large Hadron Collider is over there with the 25 petabytes per year. This is how the network is looking right now due to the LHC. It's becoming a live organism of hardware and software in communications. It's extremely important. I just want to note on the bottom right there, for those who can see it, that we actually saw by monitoring all the networks, because we have to, since we cannot keep our data on site and we have to distribute it and we monitor our networks, we saw when Syria, for example, lost their internet a couple of years ago. In the future for the LHC, what we are targeting is, in principle, real-time, alive, adapting networks that are intelligent and self-organizing in order to deal with an increase of 1,000 and another 1,000 and another 1,000 of data. So we're talking about from petabytes going to zettabytes and yoctobytes. This is huge increase in data that we have to deal with, and we have to deal with not only talking about big data, but in fact talking about smart data as well. So here's the eureka moment at the LHC. Well, the eureka moment was we made the announcement on July 4. We described all the analysis in a publication that it is available to everyone. One publication from Atlas, one publication from CMS. We had the three channels that gave us the discovery described in there, and the channels or the final states or the Higgs decays that we detected that gave us the Higgs was in 2 photons, 2 Z bosons, 2 W bosons, all bosons. This is why on the first slide I said the issue of the electroweak symmetry breaking is settled for what has to do with with the bosons. You see on the left there is the congratulatory note from Peter Higgs, who said, "Thank you for my Nobel Prize." And on the right side, we see the note we got, all the experiments. This is the note for the US CMS. You see the note that we got from Holdren, from the Office of Science, who acknowledged that the US has played an invaluable role in the discovery of the LHC in terms of not only funding and people, but in terms of all the know-how, technology that was built in this country in the past 50 years. Okay, so now we're going to see how the signal looks like. And we're going to see it in what is called the golden mode first. I want everybody to be noting, as we accumulate data, I want you to be looking at the data, and I want you to be looking at the blue histogram. The blue histogram is what I would expect from the standard model without the Higgs. Don't look at the red histogram at the moment. Look only the blue and the data. If you look at this by eye, this is why it's called golden mode, you see an excess of events at around 125 GeV. This is the Higgs. This is the Higgs decaying into 2 Z bosons. Each of the Z bosons decays into 2 muons. So you've got 4 muons in the final state, or 4 electrons in the final state, or 2 muons and 2 electrons. You analyze these, and you get the mass of the Higgs. The histogram there is if you do the theory, the simulation of the theory for a Higgs of 125 GeV, so that you can compare your discovery with some theory. And the theory you compared it there, the red, is the Higgs. In the other channel, which is not so golden, and you will see why, it's a little more difficult, it's the channel with the 2 photons. And note there, as we accumulate data, there is a little blip, which in the data minus the fit, it appears also like a little blip. This is the discovery of the Higgs in the 2 photon case. Much more difficult because the background you see, the background is the blue, is very huge noise compared to the signal. So Let's look at some event displays. The event display from the 2 photons. This is real events. The little dots and the little tracks that you see around is from reconstructing all the particles of the event in the tracker or in the calorimeter. And the 2 towers on the 2 orange towers that we have on the one side and on the other side is representing the photons. The photons are dotted because they don't leave, they're not charged particles, so they don't leave any signals in the tracker. If we look at the ones, how they look with 4 electrons or 4 muons, okay, we're going to go a little now weird here, but you see 4 tracks on the left. These are the muons. Now, on the right, 4 tracks and electromagnetic energy. These are the electrons. So the electrons look like little towers. They have little towers like the photons. And also they have tracks. And this is, in words, this is how we actually do the reconstruction of particles. We go through all the detectors and we figure out which particle leaves which characteristic signature in which detector, and we reconstruct everything together.